Hi everyone, I'm Richika, a PhD candidate at Case Western Reserve University, and I welcome all of you to the MoNuSAC Challenge Workshop. First of all, I would like to thank all the attendees, the participants, and the co-organizers who took the time to attend this event. I wish we could have met at the Challenge Workshop in Iowa, but due to the pandemic, International Symposium on Biomedical Imaging is now completely an online event. This workshop is part of ISBI 2020, and we'll present the details of multi-organ nuclei segmentation and classification challenge in this workshop. And this challenge was organized by the teams from Case Western Reserve University, Indian Institute of Technology, Bombay, and Tata Memorial Center, both located at Mumbai, India. I'll begin with the introduction of all the co-organizers. As you know that I'm Ruchika Verma and a PhD candidate in the Department of Biomedical Engineering at Case Western Reserve University. Now I'll let all other co-organizers to introduce themselves.
I'm Neeraj. I'm a research associate at Case Western Reserve University in Biomedical Engineering Department.
Hi everyone, this is Abhijit Patil. I'm PhD student at Indian Institute of Technology, Bombay, Mumbai.
Hello everyone, I'm Nikhil Korean, a PhD candidate in the Department of Electrical Engineering from IIT Bombay.
Hi everyone, I'm Swapnil Rane. I'm a pathologist at Tata Memorial Center, Bombay.
Hi everyone, this is Amit Sethi. I'm an associate professor at electrical engineering in IIT Bombay, and I've been working in computational pathology for a few years now.
Thank you everyone for the introduction. Let's begin with the motivation and importance of this challenge. Different cell types play different roles in cancer progression and treatment response. For example, some cells help the tumor cells to survive, while others are responsible for introducing proliferative characteristics, and some trigger mechanisms to cell death or apoptosis. While all these processes are responsible for tumor progressing or suppressing nature, but the exact quantification of the role of different cell types could be uncertain if we could segment them accurately. Hence, accurate nuclear segmentation classification is often the first step to assess the relative importance of the cell types. And this is often the very first step to develop diagnostic and prognostic models related to tumor progression and treatment response. The goal of MoNuSAC was to release the high-quality, annotated, multi-organ, multi-site histopathology image data to enable the quantification of state-of-the-art nuclear segmentation and classification techniques. We wanted to create a benchmark for performance comparison of generalized nuclear segmentation and classification algorithms. In this challenge, we created data from H&E stained tissue images obtained from 4 different organs. For example, here you can see breast, kidney, prostate, and lung are the organs which we used to create this data set. And the data was cropped from 40x whole slide images, which were downloaded from the TCGA data portal. Our training set included images from 41 unique patients, and we obtained 1 whole slide image per patient. And the images were obtained from 31 different hospitals. And in the testing cohort, we used images from 25 unique patients, and the data was obtained from 19 different hospitals. I also want to point out that there was no overlap between the patients of training set and testing set. We also ensured to have diverse nuclei appearances in the challenge data set across multiple organs and patients, along with the high variability in staining protocols, as you can see in these 4 images. And we obtained data in the training and testing cohort from multiple hospitals. We basically included 4 cell types in this challenge. The first one was epithelial cells. As you know that most carcinomas originate from epithelial cells, that's why we included this particular cell type. Then neutrophils, which are responsible for ingesting and destroying invaders. And macrophages, which are responsible for locating and eating particles such as bacteria, viruses, and parasites. And the fourth one was lymphocyte, which is responsible for specific responses to invaders and also produce antibodies. Tumor infiltrating lymphocytes have also been shown to be associated with clinical outcomes, and that is also specifically in lung cancer. Here I'm showing 4 images. The left one represent images before annotations and the right one are after annotations. And here you can see the tumor cell boundaries which we annotated, and the red boundaries represent epithelial cells, yellow represents lymphocytes, green are macrophages, and the blue ones are neutrophils. And similar appearance you can see, similar color variation you can see in this image. Red represents epithelial while yellow are lymphocytes. I would also like to point out the challenges which we faced while annotating these cell types. For example, here you can see that there are different cell types, for example, neutrophil and lymphocytes, which we specifically annotated, which is a subtype, which is a part of immune cells. In the neutrophil, you can see here they are multi-lobed and has a pale red and blue cytoplasmic granules in the periphery. In eosinophil, you can see it's a bilobed nucleus with the red cytoplasmic granules, and the basophil have purplish black cytoplasmic granules. In these three types of cells, you can see that there is a variation in the color and texture of the granules, which helps us to differentiate these cell types. But when you actually go and annotate these cells in the pathology images, it is very hard to identify these cell types, and specifically finding neutrophils is a very challenging problem. In this image, I'm showing an example to see different cells which I've shown here. As you can see in these two cells, they look very similar, except we can see the color variation here in the periphery, which makes this eosinophil and this one as neutrophil. And I just want to point out that it was very hard for us to identify these immune cells. This is also another pictorial representation of these three cells. I'm going to explain now the annotation protocol. We have used ImageScope to annotate different cell types. ImageScope is publicly available and is produced by Leica Biosystems and is openly available. You can download it from the link if you want to. And these cells we annotated using different layers and different colors we have used for different cell types. For example, here you can see layer 1 we used for epithelial, and we marked this as red. And in marking lymphocytes, we used yellow color, and we used layer 2 for that. Similarly, macrophages in green and neutrophils in blue. As you can see in this image, we missed some nuclei. This was okay for training cohort, but we couldn't afford this in the testing cohort because we have to evaluate your submissions. So that's why we annotated some cells with the white region and marked those as ambiguous, because it was hard to identify those cells using computational algorithms, and they had faint nuclei, and also there were some cells which we didn't include in our cell categories which we were annotating. I'm showing here the total number of cells which we annotated in the training set and testing set. As you know that we annotated 4 different cell types, epithelial, lymphocyte, neutrophil, and macrophage from 4 different organs. And in the training cohort, we had around 31,000 nuclei, which we released in the training set, and 15,000 in the testing set. And we excluded some regions which we didn't include in this count. We use panoptic quality to evaluate the submissions, and we use a threshold of 0.5 to identify whether a predicted cell is a true positive or a false positive. For example, here you can see in the left, the blue represents a ground truth cell and the red represents a predicted cell. If there is an overlap of greater than 0.5, here you can see 0.8, so this is considered as true positive. But in this case, the overlap is less than 0.5, so this is a false positive cell, and the ground truth will be counted as a false negative cell. And this is an expression to measure panoptic quality. And here we use intersection over union of the true positive cells divided by total number of pixels in true positive. And this is the formula. We have also released some codes to do some tasks, for example, to identify, to count cells from different cell types and to create binary masks from the annotation SVS files and XML files, and to create NRE masks, and also to compute PQ metric to validate your models. Here I'm showing the participation demographics. So we had total 170 registrations. Out of those, 88% were from universities and 12% from industries. And out of these registrations, we found maximum participation from China, followed by United States and India. If you want to see the exact information of the institutes, you can go to this link and you can see the visualization in the map as well. Here is a challenge leaderboard, and our winner is Simon Graham from TR Lab and from University of Warwick, followed by Shanghai Jiaotong University and Lido's Biomedical Research. A manuscript will be drafted by the organizers after this workshop, and all models which appeared in the final rank list will be described in the manuscript, and the participants will be acknowledged for their contribution through an authorship in the publication. And this information will circulate via email. And we are also accepting post-challenge submissions by the due date is April 30. And if anybody is interested to participate, feel free to register and submit your results. And if you have any questions, please write to monusac2020@gmail.com. Thank you. And I would now like to invite Simon Graham from University of Warwick to present his work.
Okay, so thanks so much to the challenge organisers for all of their efforts organising this. I know it must have taken a lot of effort, and I'm sure I speak on behalf of everyone that we really appreciate it. So yeah, my name's Simon Graham. I'm a final year PhD student at the University of Warwick in the Tissue Image Analytics Lab, and I'm going to present our solution to the challenge where we used HoverNet, which is a network for simultaneous segmentation and classification of nuclei. So this work was done in collaboration with Dang Vu, Mika Zwega, Sean Raza, and Nasir Rajput. So to give a brief overview of what I'm going to present, I'll really quickly describe the task and the data set, then move on to some of the challenges that we faced, describe our method, some of the training details, and then conclude with some of the results. So the task that we were given was to segment and classify epithelial cells, lymphocytes, macrophages, and neutrophils. Because if we're able to do this successfully, then it can help us to better understand the tissue microenvironment and can also help us to understand the role of immune cells in cancer progression. So the data set that we were given consisted of images taken from the Cancer Genome Atlas, from the breast, kidney, lung, and prostate. All were hematoxylin and eosin stained and at 40 times objective magnification. So we had around 31,000 annotated nuclei with about 15,000 epithelial cells and lymphocytes and around 600 macrophages and neutrophils. So as we can see here, there's quite a class imbalance. So the dataset was split into training and test, with 209 images from training from 45 patients and 101 images for the test set taken from 25 patients. So we can see here some example images where the red borders surround the epithelial cells, where we can see some obvious texture. Then the yellow borders highlight the neutrophils, where we can see the multi-lobed appearance. Then the green borders show the lymphocytes, where we can see there's a relatively homogeneous appearance of the pixel intensities. And then the blue border shows the macrophages. where we also are required to delineate the cytoplasm. So some of the challenges that we faced. First of all, we had to separate all of the clustered nuclei. So we can see here some epithelial cells within the image region, and many of them are touching. So first of all, we had to separate those touching nuclei. Second of all, we didn't just need to segment the nuclei, but we had to make sure that we could differentiate between the different types. So here we can see all of the types present in the data set within this image. And we had to make sure that we could effectively differentiate between these different types. Then third and finally was the presence of the unbalanced classes. So we can see here that there's just one lone neutrophil, and we had to make sure that we could still predict accurately these underrepresented classes, such as the neutrophils and the macrophages. So the method that we used was the HoverNet that was published last year in Medical Image Analysis. And the network consists of an encoder for feature extraction, and then 3 identical decoders for upsampling these features. So the encoder is a ResNet 50, and then each decoder was a densely connected convolutional neural network. So the first decoder aims to predict the binary output, or just to try and differentiate the nuclei from the background. The second branch aimed to predict the horizontal and vertical maps that I'll describe in the coming slides. And then the final branch was the nuclear classification branch that aimed to perform pixel-based classification of the nuclei. So the hover branch aimed to overcome challenge 1, which was trying to separate the clustered nuclei. Challenge 2, we tried to overcome by using a devoted upsampling branch. And then for challenge 3, which was the imbalanced classes, we used a multi-term loss function. So first we'll describe challenge 1, which was separating clustered nuclei. So to do this, we use the concept of horizontal and vertical maps. So we can see here that pixels in these maps range from -1 to 1, from blue to red. And we can also see that, especially if we look at the purple arrows, the pixel intensities or the pixel values are significantly different between neighboring nuclei. So if we can predict these within the network, then we can use that to effectively separate the touching instances. So for this, we used a multi-term loss function, where the first term of the loss function was standard MSE, or mean squared error. And the second term, we calculated the mean squared error of the gradients of the ground truth and the predictions of the horizontal and vertical maps. So now if we reuse these images from a couple of slides ago, but also show the predictions of the horizontal and vertical maps, we can see that for the MSE, for the first term of the loss function, we just calculate the mean squared error between the predictions and the ground truth. And we can see that, as I alluded to earlier, there's quite a significant difference in the pixel values between the neighboring nuclei. And there's also a change of sign. So therefore, using MSE means that there's going to be a large penalty between these touching instances. So it helps the network to focus learning in these areas. Then the second term at the output of the hover branch calculates the horizontal gradient for the horizontal map and the vertical gradient for the vertical map between, and we do that for the predictions and the ground truth. And then in the same way, we calculate the MSE. And so what this second term does, it tries to enforce the straight lines that you see in the predictions here. Then for challenge 2, we used a devoted upsampling branch to perform the classification. And if we show an ablation study from our HoverNet paper, we can see that when we use a completely independent classification branch, we can improve the overall performance. So if we look at the final column, that shows the average, this is an F score that we're showing here. If we show the average F score over the classes, we can get quite a nice improvement in the performance when we're using this completely independent branch for nuclear classification. Then third, for challenge 3, and try and solve the class imbalance issue, we similarly use a multi-term loss function at both the nuclear pixel and nuclear classification branches. So here, the first term we used was the cross-entropy loss, and the second term that we used was the dice loss. And using the dice loss helped overcome the class imbalance within the dataset. Then putting everything together, we had 2 loss terms at the output of each branch, and then overall, we had 6 loss terms to make the overall loss. So we had 3 outputs. First output was the nuclear pixel prediction, then the second output was the horizontal and vertical map predictions, and the third output was the nuclear type prediction. So we applied the Sobel operator on the horizontal and vertical map predictions to obtain the horizontal and vertical gradient maps. We then applied a series of post-processing steps to obtain the energy landscape and the instance markers, and then performed marker-controlled watershed to get the instance segmentation result. And then for each predicted instance, we utilized the nuclear type prediction to then associate the predicted category with each nuclear instance. So for some training details, we use an input size of 256 by 256 and an output size of 164 by 164. And the difference in output was because we used valid convolution in the upsampling branches. We then used rotation, flip, blur, scale, shear, and color augmentation. We used pre-trained weights on the pan-nuc dataset and used 5-fold cross-validation. So the pan-nuc dataset is a large dataset for nuclear segmentation and classification, and we thought it would be better to use this for pre-training than ImageNet because it's more specific to the problem at hand. And for 5-fold cross-validation, we ensured that when we split the data, we split it on a patient basis. Then we trained stage 1, where we only trained the 1-by-1 convolutions at the output of each decoder for 12 epochs, and with a learning rate of 10 to the minus 4. And then for stage 2, we fine-tuned the entire network for 50 epochs with an initial learning rate of 10 to the minus 4 that we decreased during training. Then we use a sliding window approach to process each image in the test set, and then averaged the results over the 5 folds to get the overall result for each image. So some example results, we can see we do quite a nice job here at segmenting and classifying the epithelial cells and lymphocytes. We also do quite a nice job here at segmenting the lymphocytes as shown in green, and we can also see that we successfully segment the lone neutrophil, which is shown by the yellow arrow. Some more results of neutrophil segmentation and lymphocyte segmentation. We do quite a nice job. And then segmenting macrophages. In these cases, we do a nice job, but overall we thought that the segmentation of the macrophages was the most challenging task. And we try and highlight this in this image here. So we can see on the left-hand side, the macrophages have quite an indistinct boundary. And so therefore, to perform this segmentation, it was really difficult. Then on the right-hand side, we see that the nuclei within the macrophages are very distinct. And so therefore, the algorithm focused on segmenting these areas, but then didn't segment the surrounding cytoplasm. First of all, we show some results for binary segmentation, so not taking into account the separate categories. And we can see the results for binary dice and binary panoptic quality for each fold. Then we show the multi-class panoptic quality results. So there might have been a difference in the way that we calculated the PQ and how the organisers calculated the PQ, hence why we've got some lower results on the slide here. And then we show here some results of using pan training. So we can see for especially the multi-class case, we can increase the performance slightly by using this strategy. So looking forward, we want to try and improve the performance of macrophage segmentation and also extend the model to additional cell types, such as more immune cells and other cells such as fibroblasts, and maybe even differentiate between malignant and non-malignant epithelial cells. And then overall apply it to whole cell images and try and further understand the role of immune cells in the TME. So thank you.
Great, thank you. Very good.
Are there any questions?
Hello, my name is Hyun Jung. Thank you for the great presentation. I have a quick question regarding the color difference between the training and testing images. Did you try anything in order to overcome the challenges of color profile difference between the training and testing images?
So what we did was we performed color augmentation. So we didn't do anything like stain normalization or even stain augmentation. We just simply perturbed the values of the images in terms of their hue, saturation, contrast, and brightness. And that helped to overcome this difference in the color appearance.
Got it. Thank you.
Jinming Duan has a question. Can you read it in the chat, Simon?
Okay, how do I go on to that? Here we go.
How did I get it? So I think at the bottom, you'll see a chat.
Yeah, I'm on it now. I'm not sure whether you can see my window, but I'm reading it.
Okay.
Okay, so I'll repeat the question. So thank you for the talk. I have two questions. First of all, can the post-processing be learned to end-to-end? And then the original unit paper used weighted cross-entropy, I'm guessing you're talking to here. So first of all, I haven't personally seen a solution where you incorporate the post-processing within the network. Standard procedure is to apply that at the output of the neural network, because you're going to get a raw probability. So therefore you need some way to convert that raw probability to a prediction. So in terms of learning it end to end, we haven't tried that, no. Second of all, did we use weighted cross entropy, which is I'm guessing what the question is here. It's been used in other problems that we've been involved in, but we didn't use it here. So it mentions putting more edge on the weights on the edges. So the MSE also helps to focus more edge between the touching nuclei, because as I alluded to earlier, there's differences in the pixel values. So therefore, naturally, the MSE will focus in these areas. So we didn't need to use the weighted cross entropy in those areas specifically. Okay. Shall I move on? Should I stop showing my screen?
Any other questions?
Sorry, I have a question. Can you hear me?
I can hear you.
Hi, Simon. It's Amir Reza. I have a question. When you said that you pre-trained your network with this pan-nuc dataset, how many classes that you have in this specific dataset that you use for pre-training? Was it the same like this challenge, or it was different?
So I'm just trying to think how many classes it was. It was either 4 or 5 classes, and the categories were different. So the categories there were, it broke down into epithelial, neoplastic, connective tissue cells, and inflammatory cells. So the categories were different. And so therefore, because there was a difference in the number of classes, that was the reason for having to train initially the one-by-one convolutions at the output of the network initially before we fine-tuned. Does that make sense, Amareza?
Yeah. Thank you for the answer.
Okay, so the question is, these are images that have variable dimensions. How did you solve this? So yeah, good question. So we used a sliding window approach, and if the image had smaller dimensions than the patch size that we used, then we used reflective padding before applying that sliding window approach. And then what about, yeah, so I think I've answered that final question as well. So we use reflective padding to deal with images smaller than 256 by 256. Okay. Should I stop sharing my screen now?
I think, yeah. Thank you, Simon, for the presentation.
No problem.
Our second participant is not available because of the pandemic situation, and I'll try to share his presentation.
Good morning, everyone. My name is Wu Xiyi. I'm from Shanghai Jiao Tong University. I'm very glad to have this opportunity to present my algorithm of the challenge, multi-organ nuclear segmentation and classification. My presentation will include these 3 parts. First, introduction about this challenge. Second, the main methods we used. And the last, the results we got. First is the motivation. Different types of cells play a vital role in the initiation, development, and invasion of tumors of various organs. For example, most carcinomas originate from epithelial cells, and tumor-associated macrophages influence diverse processes. Thus, accurate identification and segmentation of nuclei is important for AI-enabled characterization of tumor and its microenvironment. In this challenge, organizers provide H&E stained digitized tissue images of 4 organs with annotations of 4 cell types. In total, the training set contains 31,411 hand-annotated nuclear instances. This picture shows an example of annotated images. The third one is masks generated from the annotations, and different types of cells are marked with different colors. We need to use the annotated dataset to develop algorithms to recognize these cell types from the tissue images of unseen patients released in the testing set of the challenge. Nuclear segmentation and classification are both challenging tasks. Firstly, instances get crowded together without obvious boundaries, making it hard to segment individual nuclei accurately. Secondly, the fine-grained classification of nuclei is also difficult due to the large interclass and intraclass variances in nuclear shapes and textures. Thirdly, as shown in the chart, the amounts of annotated instances of the 4 cell types varied a lot, which encourage us to develop algorithms for learning from imbalanced classes. Next is the part of methods. First is data preprocessing. Color normalization is performed on all images to remove the color variations of different organs. Then we extract patches of size 250 times 250 uniformly from each training images with overlap of 40. For each patch, a 224 times 224 image is randomly cropped as the training data. Other augmentations include random scale, random horizontal and vertical flip, random affine transformation, random elastic transformation, random rotation, and normalization with mean and standard deviation by channel. To separate touching nuclei, one channel is used to predict the contours of nuclei. Therefore, we dilate the ground truth mask using a 3x3 kernel with iteration of 1, then do subtraction operation to get contour labels. As shown in the picture, nuclear contours are in white. Next is the overview of our framework. A 2-level deep neural network is proposed, informing global configuration and accurately describing local appearance, respectively. In the global stage, we achieve nuclear instance localization in a per-pixel prediction fashion. The nuclear localization network outputs 3 probability maps: backgrounds, inner parts, and contours of all nuclei. In this way, nuclear regions of interest can be cropped from the original image. Then in the local stage, VGG16 and ResUnet are used for classification and segmentation of nuclear regions of interest, respectively. Then in the last step is mapping nuclear instances, segmentation, and classification results back to the original images. The nuclear localization network consists of 2 parts: the prediction network that generates the segmentation masks of all nuclei, and the perceptual loss network that computes the perceptual loss between the predicted label and ground truth label. The prediction network is the routing encoder-decoder structure based on UNet. We utilize the powerful representative ability of residual networks to extract features. The encoder is from ResNet 34 without the average pooling and fully connected layers, and is initialized with the pre-trained parameters from image classification tasks. There are skip connections between encoder and decoder, which helps to recover high-resolution feature maps. The contour map in the prediction mainly aims to capture the contours of crowded and touching nuclei. As a result, the predicted inner parts of each nuclei are not connected. Then we can obtain each individual nuclei without much extra effort. The perceptual loss network is utilized to improve the segmentation accuracy of details in the image. The pre-trained VGG16 model is a feature extractor and is fixed during training and test. 4 levels of features are extracted using this network for the output of the prediction network and the ground truth label. Then the mean square loss is then computed between the feature sets of the two inputs. The loss function consists of two parts. The first part is the perceptual loss just mentioned, and the second part is weighted cross-entropy loss for 3 classes. In order to alleviate the problem of class imbalance, we assign larger weights for low-frequent class pixels. The formulation is as follows. While D1, D2 are the distances to the nearest and the second nearest nucleus. In addition, we set sigma as 5 and W0 as 10 in our work. For nuclear classification, VGG16 is used to classify nuclear ROI into 4 types of cell and non-cell patch. The non-cell patches are considered as false positives. For example, the ROI containing incomplete cell needs to be removed. Then we use focal loss during optimization to focus training on a sparse set of hard examples. Considering the class imbalance, the weight of 5 type is 2, 2, 4, 4, 1. As for the task of nuclear segmentation, ResUnet and cross-entropy loss are used for fine instance segmentation. Finally, we can obtain the segmentation and classification results of their instances and map ROI back to the original image to get the final results. The last part is the experiment results. The metric adopted for evaluating our performance is weighted average of the class-specific panoptic quality. If the IOU of predicted nucleus and the ground truth nucleus is strictly greater than 0.5, the predicted nucleus is classified as true positives. 5-fold cross-validation is used in our experiments. Then the best 3 models are used for testing, and the average prediction of them are computed as the final results. Last row in the table is the score we got on the testing data, showing the robustness of our methods. That's all. Thanks for your listening.
I would like to thank CEU for sending her pre-recorded video. Now I would like to invite Yanling Liu from IVG Lab to present his work.
Hi, this is Yanling from Frederick National Lab. So for today's presentation, my colleague, Dr. Hen Zhang, will present his work for this MoNuSAC segmentation challenge. He did the most of the work.
So my name is Hyun. Can I share my screen?
Yes, please.
Sure. Can everybody hear me?
Yeah, we can hear you.
Yeah. Okay. I'll start the presentation. First, I wanted to thank the organizer for organizing this challenge. It was a great experience.
Hi. Can I interrupt? I think your the screen that is showing to us is the one where you have.
Oh.
Yeah.
Sure. I'll swap the display.
Yeah, this is fine. Thank you.
Sure. Thank you. So the title of my presentation is Utilizing Domain Adaptation and Pseudo Labeling for Multi-Organ Nuclei Segmentation. Our team is myself and Chitam Brown and Yang Ni. We are from Frederick National Laboratory for Cancer Research. And this is the content for today. We're going to briefly explain what are the challenges that we encounter while participating in this challenge. And then we're going to also present how we address these challenges, and then results and acknowledgement and references. First of all, I believe the most severe challenge, most difficult challenge that I encountered while participating in the challenge was the noticeable gap between this data distribution in train and testing. So the images on your left are the images from the train data set, and the images on the right is actually from the images from the test data set. As you can see, there's a obvious color profile difference between the train and testing images. And as previous presenter already mentioned, that there was a class imbalance between the 4 different classes, epithelial, lymphocyte, neutrophil, and macrophage. And also we have to segment or identify what are the background pixels. And then as you can see, number of background pixels is about 250 times greater than the number of pixels from the neutrophil. And then within this epithelial, lymphocyte, and neutrophil macrophage, there was another class imbalance as well. And this is our proposed method. First of all, this is how we prepare our data. So our patch size was 256 by 256. And then we extracted patches with a sliding window fashion with a stride of 64. So it was overlapping patches. And then we did 5-fold cross-validation. And then each fold was composed of 80% of trained data and 20% of validation data. And then there were some of the images that are smaller than our patch size. So in this case, so the picture on the bottom left is the trained images that are smaller than 256 by 256. So in this cases, we padded with white ground pixels and then make them padded with white pixels so that their size is equal to 256 by 256. And we use albumin, So we use augmentation library in order to pad those pixels. We also apply data augmentation. We did apply data augmentation on the fly, which is called online augmentation. So when each batch is fitted to the network, we apply augmentation. So we believe this helped us prevent overfitting our network. So in turn, we'll explain more later in detail, but we did utilize unsupervised domain adaptation. So during the training process, training images and then testing images are fed to the network at the same time. So in terms of training images, we apply 8 different data augmentations. Each augmentation is numbered 1 to 8, and the corresponding resulting images are displayed on the right side of the slide. So when the shift, scale, rotate data augmentation is applied to the original images, their resulting images are shown here, and the rest of the augmentation results are also displayed on the right side. And for the testing images, we apply only 4 different augmentations: shift, scale, rotate, horizontal flip, vertical flip, and transpose. We also utilize the augmentation library for data augmentation. And in order to, as I previously mentioned in the slide, in order to address the color difference between the testing and training images, we used unsupervised domain adaptation. And the method that we use is called advanced method. Is the main objective of this method is to minimize the entropy. So this is the main idea, how the domain adaptation is applied. So this is the figure which we get from the paper, which is shown in reference 5, which will be shown in the last slide. So if there's a difference between a source and target data, their prediction is going to be different. So source images, which is training images, their predictions are very clean. You can only see the high entropy on the boundaries. But when you apply those trained network and predict target images, their prediction is very noisy. So if you see the entropy map, their entropy map is very noisy. As you can see in this area, their entropy values are very high, which leads to the noisy prediction. So their main idea was to lower the entropy from the prediction map, which is shown on the bottom left. So entropy means basically the randomness of the prediction. So the randomness of the prediction gets lower, and then that will lead to the cleaner prediction. So this is our proposed network. We use a single network. As a backbone, we utilize UNet. And for encoder, we utilize ResNet 50 layers. And this ResNet 50 layers includes squeeze and excitation blocks. And we didn't implement this network from the bottom. We utilize a segmentation model PyTorch. So our platform, we utilize PyTorch as our training platform. And we utilize the train model. So as you can see, during the training process, source images and target images are fed to the network at the same time. So we utilize two loss functions. The loss function, first loss function is source segmentation loss minimization, which is to minimize the prediction versus sources label. And at the same time, the target images are fed to the network. And then we calculated Shannon's entropy of the testing images. So as you can see, during the training process, there are regions of interest that are showing the high entropy values. So our second loss function was to, objective of our second loss function was to minimize those high entropy values in the testing images. And then we also utilize the pseudo labeling. So pseudo labeling basically means that choose the target images with low entropy values, which means that the target image prediction was confident. The model was very confident with the target image prediction. So we chose target image with low entropy values, which was 0.05, and then use this prediction as a label. And then include them in the training process. So after training source images first, and then we inference all the target images, and then we calculate each target image's entropy, and then we choose the lower entropy value target images, and then use their predictions as a label. So during the second phase of the training, we include source images and then target images at the same time. And then we also utilize the original target images to lower the entropy values as well. And this is the hyperparameters that we utilize for training a network. Maybe a few things to be noted was the loss function. So we, in order to address a class imbalance, we utilized weighted cross entropy function. And then we also utilize robust softmax loss. This is loss function that made the dice coefficient differentiable. So basically, you can regard this. You can think of this as a cross entropy plus the dice loss. And then also we utilize the nuclei boundaries. So we modify the original annotations and include the boundaries of the nuclei. And this is also, we have utilized the test time augmentation. So after the training the network, when we inference the testing images, we not only inference the original testing images, but we also inference the augmented testing images. So we inference the original images and then rotated images, and horizontal and vertical flip and transpose testing images. And then we average those 7 predictions, and then we finalize our testing image prediction. And we ensemble the network. We chose 5 highest validation PQ scores, and then we ensemble these 5 different networks. And here are the results. So in the previous slide, I mentioned we tried to minimize the entropy of the target images. So on the left side of the figures, these are the testing images. And then the B is corresponding entropy map. And then C is their corresponding prediction. As you can see, the left images, they have high entropy values, and then their prediction, as you can see in the C on the left side of the figure, is noisy. Within the one instance, there are different classes coexist, which is obvious sign of the noisy prediction. But on the other hand, when you see the right side of the figure, A, this is a testing image with low entropy. So and then B is the corresponding entropy map, and then C is their prediction. As you can see, the testing images with low entropy value, their prediction is relatively cleaner than the entropy value with high entropy value testing images. So I think this images show you that the lowering the entropy value actually helps to address the difference between the color difference between the training and testing images. And this is our final prediction, one of the testing images prediction. And our final PQ score was 0.50. And this is the acknowledgement slide. And this is the reference that I utilized in this work. And this is the end of my slide. Thank you. Is there any questions? I'll be happy to answer them.
Can I ask a question, please? It's Simon here.
Sure.
Could you please go back to the slide where you're showing the stain variability between the train and test?
Sure. This slide?
Yeah, so here, I'm pretty sure that the reason why there's a difference here, it's not necessarily because of the stain, but on the left, you've most probably got RGB, and it looks like it's BGR on the right-hand side. Because if you look, there's some regions that most probably should be red, and they're very distinct blue. So I think the color channels are just mixed up here.
Oh, you're saying the testing images, their RGB channels are mixed. I mean, not in the correct order.
So I can't remember now if this is actually how they appeared in the test set, but what I can see here, that it very much looks like it's RGB on the left and BGR on the right-hand side.
Oh, I see. So this is actually the testing images look like in the.
Oh, okay. Well, in that case, they must have been muddled up a bit. So it looks like it's BGR on the right-hand side.
I see. I see. Ah, maybe. Yeah, I was very confused why these testing images look like this. So maybe if we rotate the channels, then it should be looks more like train images then.
Exactly.
Okay. Thank you.
Are there any other questions?
Yes, may I ask a question?
Sure, please go ahead.
Okay, I'm wondering to know what is the main difference between your first submission and second submission? I think you had 2 submissions, if I'm not wrong, right?
That's correct. That's a good point. So at the first preliminary results, there was a error in the inferencing the testing images. There was a initialization error. So I fixed those errors, and then I tried to. The initial preliminary network, our algorithm was very complicated. So our preliminary result, there was 3 different networks trained at the same time, which was very complicated. So after submission of the preliminary results, I tried to reduce the complication of my network. So I just trained single network and then fixing the error, and then the score went up a lot. So the lesson that I learned from this challenge was that complicated network is not always better. And yeah, that was my lesson.
Okay, thank you.
Sure.
Any other questions, please?
There's something in the chat, I think.
Oh, chatting.
Lucy. Oh, okay.
Let me see whether I can check the chat.
Yeah, so astute observation, Simon. In the lower left panel of the test, the blue seas of all is most likely red blood cells. So yeah, that's to Simon's point that the color channels might have been swapped.
Right. I believe I agree with them. Yeah. The blue sea is most clear, red blood cells. Yes.
Are there any other questions?
All right, then let's move on to the next presentation.
Okay. I would like to thank Hyun for the presentation, and our next participant from NVIDIA University, China is not available, and she couldn't send her pre-recorded video because of this current pandemic situation. I would like to invite Syed Ali Reza Fatemi Jaharumi from Sharif University of Technology, Iran, for the next presentation.
Thank you very much. So let me first share my slides. Do you have a clear view of the slides?
Yeah.
Hello, everyone. I hope everyone is in good health. I'm Syed Reza Fatemi Jahrami from Sharif Hushbardas Group, and I'm delighted to be here today to talk to you about the methods and techniques we use in this challenge. My teammates are Mr. Ali Asghar Khani and Mr. Hassan Montaghi, and we worked under the supervision of Professor Hamid Behrouzi and Professor Mahdi Soleimani. Through this presentation, while discussing each step of our algorithm, I will tell you the difference between each version so you may fully understand all the things that we tried between each version of our algorithm. So this presentation will probably take 10 minutes, and let's start. Our method consists of three main parts. First, I'll start with preprocessing. Next, we'll move on to model selection and training. And finally, I'll talk about post-processing. So I will discuss these steps in detail, and in the end, I'll show you the score that we achieved and some of the results that we produced. So the first step is preprocessing. We applied these steps to the given data set. First, we normalized the colors in the slide, and then we generated borders for each cell in the slide. Next, we created a heat map to mark the essential parts of the slide. I will explain later how we use this heat map. Afterward, we split the data into a training and validation set, and then we added padding to slides and patched them. And finally, we applied data augmentation. So now I will dive deeper into each of these steps. So we used Vahten stain normalization method to omit the stain variation residing in the histopathology slide. On the left side of this page, you can see the slide we used as the target in the normalization process. And on the right side is an example of the normalization applied on another slide. We applied this step in all versions of our algorithm. So in the next step, we generated borders for each cell in the slide. We use these borders as the sixth class along with the other 5 classes being background and the cell types in our semantic segmentation task. We added this step in the final version of our algorithm. In the first version, we did not include the borders in our mask. So our mask only contained 5 classes being background and the 4 cell types. Next, we generated a heat map and used this heat map to reweight borders to emphasize on the edge of dense regions. So the neural network learns more to distinguish between cells that have overlap. This step was also added in the final version of our algorithm. For training the neural network, we needed validation data set. For this purpose, we split the data into validation and training. This splitting is done in a patient-based manner, and the ratio of the number of any cell type in the training data set compared to the number of the same type of cell in the validation data set is approximately 4. So in the first version of our algorithm, we did not do this split in a patient-based manner. So in the second version, we considered the patient. So because of the variation in the trained slides, in the resolution of the trained slides, we zero padded each slide so that they can be patched into patches of size 512 by 512. And we did this patching with an overlap of 128. Also, this step was the same in all versions of our algorithm. And for the last step in preprocessing, we augmented data to make the network more robust and to enhance data. These are the augmentations that we applied: random horizontal and vertical flip, adding random values to the pixels, random Gaussian blur, adding random values to hue and saturation channels, changing the brightness and contrast of images, elastic transformation, and random rotation and translation and scaling. So here you can see an example of applying some of these augmentations on a sample slide from the training set. The original slide is on the top left. So to wrap up the preprocessing pipeline for the final version of our algorithm, the input of our neural network, which I will discuss later, are patches of size 512 by 512. And the ground truth for these patches are multi-class masks containing the borders, the background, and the 4 cell types. We also generated heat maps using cell borders to emphasize more on the edge of the dense regions while training our neural network. So now we have reached the training phase in which I'll describe the different models that we used and our final model, and also the loss and the optimizer. The model that we used in the first version of our algorithm was DeepLab version 3+. And for the backbone of this model, we used a modified exception that was pre-trained on ImageNet. And for the final version, we used a feature pyramid network, or FPN, for semantic segmentation. And for the backbone of this network, we used EfficientNet, which was also pre-trained on ImageNet. So here you can see an overview of the architecture of feature pyramid networks. And we used add operation for the pyramid net for the features that was extracted. For the loss of the network, we used weighted categorical cross entropy, and in the final version, we multiplied the loss by the heat map that we generated in the preprocessing step. And as you can see, for the optimizer, we use Adam optimizer with the learning rate of 10 to the power of -2. And we freeze the pre-trained backbone and then train the model. So to sum up our model selection and training, in the first version of our algorithm, in which our masks did not have borders, we used DeepLab version 3+. And in the final version, in which we included borders in our masks, and also used heat maps we generated in the preprocessing for weighting our loss, we chose a feature pyramid network. So now we have reached the pre-processing part. This part was an essential part of our work. In this part, we use various methods to further increase the accuracy of our method and transfer the semantic segmentation output of our model into an instant segmentation result. The pipeline we used consists of these steps: test time augmentation, cell splitting, dense CRF, and voting for cell type. So we didn't have multiple networks for ensembling, but test time augmentation helps us ensemble multiple predictions. 8 images, we provided 8 images using the 90-degree rotation, horizontal flip, and vertical flip. And the mean of the network's output for all of these images is the final prediction. So we used test time augmentation in the final version of our algorithm. So for cell splitting, we did this. The first channel of prediction is the probability of background. So obviously 1 minus this channel gives the probability of foreground. Also, the boundary channel in the prediction helps us sharpen this foreground and create a neater input for the next step. As you can see, the boundary removing converts the image in the center of this slide to the image on the right side, in which the cells are better split. And finally, we used a watershed algorithm and morphological operations, such as opening, to separate the cells. So in the first versions of our algorithm, we tried using dense CRF, but we did not succeed in improving the results, and it also increased the time needed for preprocessing by about 10 times. So finally, we decided to exclude it from our post-processing pipeline in the final version. And for assigning a label to the cells we split in the previous steps, we used a voting mechanism. The score of each label is the sum of the probability of related type over pixels of the cell. And the final label is the type with the maximum score. So up until now, I've talked about the main points in processing, model selection and training, and post-processing of the first and final version of our algorithm. In the next slide, I will show you the score we achieved and also some outputs that we produced. So here you can see the score each version of our algorithm achieved, and also an overview of key parts of each version. And here are some examples of the output of the final version. So that brings me to the end of the presentation. Thanks everyone for your attention. Now I'll be glad to answer any questions that you may have.
Are there any questions?
I have a question. Did you do any ablation study to compare color normalization with, let's say, color jitter? And did you find one better than the other?
No, we didn't compare those. We in all versions we just applied state normalization. We didn't try a version without normalization.
Thanks.
Okay, I have one more question. Thank you very much for the nice presentation. You said that you apply test time augmentation in the inference phase, yes. And you apply, for example, something like rotation or flipping. I'm wondering to know, for example, when you rotate a test image, then how do you actually fuse the results from the original test image and the rotated test image? Because now the coordinates are not same, so you cannot, for example, take the average over the results. So how did you do that?
The rotations that we applied are 90-degree rotation and horizontal and vertical flip. So just by reversing the steps, there's no problem. You can just take the mean of the outputs by doing the reverse of the steps you did.
Okay, so for example, you rotate the image for like 90-degree, and then you rotate it back to the original image coordinates, right? Something like that?
Yes, right.
Okay, thank you.
Sure. Are there any other questions?
Thank you, Alireza, for the presentation. Our next speaker, Pavel, is not available. He's
sorry, Ruchika. Can I say?
Sure.
Yeah, actually, hi everyone. Actually, Pavel is here, but he occasionally got sick yesterday, and he cannot speak, unfortunately. And I can suggest just play his recording, and he can answer all the questions in the chat. Will it work?
Yeah, sure. Thank you. I'll play a video for that.
Oh, okay. Thank you.
Okay.
Pavel, and my team is Experience AI, and today I'm going to present to you our algorithm developed for participating in MoNuSAC 2020 challenge. Let me say a couple of words about the challenge. In MoNuSAC 2020, participants are provided with H&E stained tissue images of several organs with annotation of 4 types of cells. The aim is to provide a computer vision algorithm which can successfully segment and identify the cells in previously unseen images. During the report, I'll mention the following aspects. First, architectures of models. During the research, we tried a number of different models. Basically, our models consist of encoder and decoder. I'll give a brief description of used ones, and also I'll mention novel shape attentive UNet, on which we also had some hopes. Second, training process. I'll give a description of preprocessing steps, mention the influence of augmentations, and list used up optimizers and loss functions. Third, the most important step there is post-processing, since we had to convert semantic segmentation predictions into instance ones, which is not a trivial task. At last, I'll show the achieved results. Actually, we started our experiments with ResNet 18 as encoder and used it as a baseline. It is worth mentioning that the combination of ResNet 18 and UNet gave us around 0.5 mean intersection over union, and it is actually quite good. Then we continued our experiments with deeper ResNets, ResNexts, DenseNets, and DPNs. For example, in a plot with different decoders, ResNet 50 was used. Overall, we came to the conclusion that choosing an appropriate encoder can slightly improve the final quality, but the main role belongs to decoders. Finally, after a series of experiments, we focused on DPN92. Dual-path networks were originally proposed 3 years ago and led to significant improvements in scores over previous models like ResNext and DenseNet on popular classification datasets such as ImageNet 1K. Moreover, DPN achieved state-of-the-art while also having less parameters. For instance, DPN92 outperforms ResNext 101 while having approximately 15% fewer parameters. DPN picks advantages from both ResNet, which forces model to reuse gained features, and DenseNet, which allows to explore new features. By concatenating these two approaches, DPN, with the help of dual-path architecture, shares features from layer to layer and still has the opportunity to discover new ones. You could see the architecture in the slide. We also decided to use this model because there was an idea that gaining rich feature representations will help the decoder to clearly interpret an original image and to give precise predictions. Also, we used 4 different decoders during our experiments. Overall, fully convolutional neural networks achieved great success in semantic segmentation tasks. So we started with basic UNet, which was originally developed for medical image segmentation. Over time, the UNet architecture was developed and improved, which led to the appearance of such methods as LinkNet, FPN, and PSPNet. In the slide, you could see the difference between UNet and LinkNet. The second one used addition instead of concatenation in skip connections. As for PSPNet and FPN, they were originally designed to solve the scene passing task. These models try to utilize the global context of the scene and correct their predictions with respect to this information. We decided to use these models as tissue around different types of cells is not the same, so context information could boost the results. However, approaches which have proven their effectiveness in scene passing weren't successful in medical segmentation tasks. This is because of different distribution of stained images of various organs. In the plot, you could see that FPN and PSPNet achieve much worse results, 0.55 and 0.45 mean EIU corresponding. And LinkNet and UNet results are almost the same. Actually, LinkNet achieved a bit higher at last, but the second model shows higher stability during training. Also, we tried novel shape attentive UNet. Actually, it is a combination of 2 streams, the texture and the gated shape stream. The core idea is to utilize feature representations of objects for additional predictions of shapes and borders of the cells. The texture stream actually is a simple UNet with DenseNet 121 as encoder. The gated shape stream handles feature representations from the texture stream and refines relevant boundary and shape information. Authors use gated convolutional layer to merge the information from both streams. We decided to compare SoundNet with such models as DenseNet 121 plus UNet and ResNet 50 plus UNet. Overall, we came to the conclusion that using shape attentive UNet is impractical due to First, comparable results with traditional UNet. Second, time and memory costs. SoundNet requires 3 times more time and 2 times more memory for training compared to ResNet 50 plus UNet model. And last, hard-coded encoder. Unfortunately, we didn't find the way to use SoundNet with another encoder, which led to loss of flexibility in our experiments. At last, we decided to focus on LinkNet and UNet decoders, and after a series of experiments, we found that the combination of UNet and DPN92 is the most successful. Our final architecture is five-stage UNet with dual-path network pre-trained on ImageNet plus 5K used as encoder, which batch normalization and ReLU activation function. So in order to boost the results, we had an idea of using cells borders as an additional input channel. It is a popular approach nowadays. The borders are received with help of traditional computer vision algorithms and morphological iterations. Unfortunately, we faced some issues. Usually, to utilize border, images are thresholded, skeletonized, edges are gained with the help of some methods, for instance, Kenny algorithm. A few different morphological operations are applied on image and so on. After that, the width of the contours is then calculated with respect to the cell's area, and these borders are passed into the network as the next channel with information to improve final predictions. However, in our case, we could not find appropriate general thresholding politics. As images in the dataset have different distribution of colors, we could not build a common algorithm to successfully distinguish cells. In the slide, you could see the example. If we try to threshold these images with the same politics, it will fail in one case. Moreover, different cell types also have different colors, and it is an additional issue. Overall, during training, we fed 320 on 320 images as input, and during inference, images were padded until their shapes are divisible by 32. The padded images were passed through the network, and then the center crop to original size was applied. As the size of the dataset is limited and models require a lot of data to train well, actually much more than we have, we used augmentations to artificially increase the dataset. We used quite a standard set of augmentation techniques: random flips, shifts, scales, rotation, adding some noise and changing saturation, hue, brightness, contrast. We added extra blur and gamma. The most interesting situation was with the elastic transform. This augmentation led to significant decrease in quality. We think that this is because after the augmentation, cell shapes are deformized, and therefore it becomes difficult for the neural net to distinguish them. Model learns to find cells of a certain form, and the elastic transform just adds a mess. In the slide, you can see the influence of augmentations on mean EIU. Overall, augmentations increased our metrics from 0.6 to 0.625. The model in the plot is DPN92 plus UNet. Also today we have plenty of different optimizers to train our models. The widespread choice is Adam, but there is also its modification called Adam Mod and other options, such as DiffGrad, Ranger, and so on. We tried the mentioned ones, and the results could be seen in the slide. You can see that the behavior of models with different optimizers isn't the same. Models with Adam and Adam Mod tend to reach its plateau much faster, and models with DiffGrad and Ranger are slower. Also, final results of models with the last two optimizers are significantly worse. Overall, Adam is still the best choice for models training, as it shows the best results and ensures the fastest convergence of the model. Probably the results of DiffGrad and Ranger could be better if we performed hyperparameter tuning, but we didn't. As for loss function, the widespread one for training segmentation models is dice loss. In our work, we also used it. We choose it as dice loss shows really well in case of an unbalanced dataset, which is our art. However, dice loss is usually combined with other functions in some proportion. We tried to combine it with binary cross entropy loss and novel active control loss in proportion of 0.7 to dice and 0.3 to another function. In the plot, you could see the results. Standard PCE loss achieved 0.625, while the model with active control loss got 0.6 mean ARU, and therefore we choose binary cross entropy. As our model gives us binary masks for each class and we need to separate each instance, the post-processing steps are required. There is a well-proven traditional computer vision algorithm called watershed. It is an algorithm for segmentation which helps to separate touching or overlapping objects, especially when they have circle or elliptic shapes. If the watershed is applied to an RGB image, the image should be binarized, but our predictions are already binary. However, we still should apply some steps to get markers for the algorithm. Actually, we used a marker-based watershed algorithm where you specify markers and the algorithm flows volleys, starting from the markers and moving outwards until the volleys of different markers meet each other. So as markers, we actually regard centers of the predicted cells. To find centers, we firstly apply a number of morphological operations, such as erosion and dilation, in order to suppress the noise and create a distance between contiguous cells and make it easier for watershed to separate them. After that, we calculate the distance from every pixel with value 1 to the ground with value 0. This gives us a heat map in which we find local peaks. These local peaks are treated as centers of cells. However, if you try to use the centers as markers for watershed, you will face lots of false separations. Algorithms tend to consider a single cell, which is spatially elongated, as succulent ones, and split them, which leads to low quality. In order to suppress it, we apply dilation with a cross-formed structuring element and make centers larger. It improves the situation, but still there is a number of excessive splits, which could be seen on the next slide. In the slide, you can see a visualization of our final predictions on the validation dataset. The first row is images, the second is ground truth masks, and the third is predictions. In the left column, there is an example of almost excellent prediction, and in the second one is a failure case. As you can see in the left images, the model successfully found all instances, but gave one false positive prediction. Actually, I'd say that in image there is something similar to a cell in the area of false positive prediction, so model found it. And in predictions on the right, there are a number of false negatives and excessive splits. The cells in images obviously belong to different classes, and there are much fewer instances of cells from the second image in the dataset, so it is much harder for the model to predict them. As for metrics, our approach was evaluated on challenge test dataset and achieved 44% average panoptic quality, which gave us 6th place in the leaderboard. Overall, our approach is quite straightforward but still efficient and potentially can be used in real practice. Thank you.
Thank you, Ruchika. Thanks, everyone.
If anyone has questions, please ask. Either you can type in the chat box or ask verbally. If there are no questions, I think we are good. Okay. we are good to move to the next presenter.
Thank you, Alex and Pavel, for the presentation. Our next presenter, Ujjwal Bad, has a poor internet connectivity, so he requested us to present his pre-recorded video. So I'll share that.
Greetings to all. I am Prasad Datande from Sri Guru Gobind Singh Ji Institute of Engineering and Technology, Nanded, India, presenting this presentation on behalf of me and my other team members. Other team members are Romil Lodaya, Ujjwal Baid, Bhakti Baheti, and Dr. Sanjay Talbar. The proposed work is entitled as a multi-CNN approach for nuclear segmentation and classification. This is the table of content for the presentation. With the improvements in hardware and software, digital pathology has risen its popularity and has become a major revolution in modern medicine. Whole slide images acquired with highly automated scanners are widely used in broad range of applications in clinical practice. In this regard, to utilize the rich data available in whole slide images, MoNuSAC 2020 challenge provides hemotoxylin and eosin stain images of multiple cell types. The dataset includes annotations by experts for epithelial cell, lymphocytes, macrophages, and neutrophils. The challenge aimed at developing a computer vision algorithm for automatic segmentation and classification of these types of cells. In this era of technology, the developed algorithm will be an important tool that can assist the pathologist in analyzing whole slide images. The motivation of our proposed work is shown here. Different types of cells in human body play a vital role in initiation and development of tumors in various organs. Most of the carcinomas originate from epithelial cells. This is the reason to consider epithelial cells in this task. Lymphocytes are associated with clinical outcomes of several deadliest cancers like breast, prostate, and lung cancers. Tumors that are associated with macrophages influence various processes such as angiogenesis, mitogenesis, etc. Therefore, accurate identification and segmentation of nuclei of multiple cell types is essential to study characteristics of tumor and its surrounding tissues. In this slide, we describe the given dataset. The training cohort provided by the MoNuSAC 2020 challenge contains total 209 images. These images are collected from 4 different organs that include breast, kidney, lung, and prostate. Each image in the dataset contains at least one type of nuclei which are annotated by clinical experts. The images in given dataset are of variable dimensions. The range of width dimensions W varies from 81 to 1956, whereas the height dimension H varies from 74 to 2162. The cell count in total images is shown in table 1, and figure 1 shows the example of stain images from given dataset. These figures also shows the annotated marking of desired 4 cell types. We found 4 challenges when we analyzed the dataset. These challenges are listed here. The very first challenge is high class imbalance. That is from table 1 we can observe the cell count of cell for each type. The cell count of macrophage and neutrophil is 28 times lesser than the cell count of epithelial and lymphocytes. In addition to this high class imbalance in total dataset, we also found the class imbalance in single images also. For example, image shown in figure 2D shows that there is high cell count of epithelial cell, whereas there are no cell or few cells of other types. The second challenge in dataset is very high variation in stain colors, which can be observed in figure 2. The other two challenges are variable dimensions of images and overlapping cells. Referring to these mentioned challenges, we developed our methodology for proposed work. The first step included in our methodology is data pre-processing. The data pre-processing consists of 4 stages. The first stage involves task division and data distribution. Due to the problem of high class imbalance, we divide the whole task into 4 subtasks based on cell types, that is E, L, M, N. With this, we were able to focus on each cell type independently. This not only solved the problem of class imbalance for us, but also the problem of overlapping cells too. The data distribution for each cell type is given in table 2, which will be discussed further. The second stage of data pre-processing is stain normalization. To overcome the problem of color variations in images, we use stain normalization technique proposed by Vardhane. Since we divide the work in 4 tasks, we chose 4 images based on 4 dominant classes for stain normalization. The third stage is patch extraction, in which we extracted the patches of size 256 by 256 by 3. There are also images with dimensions less than 256 in the dataset. For such images, we padded the image using mirror padding as shown in figure. The last stage is data augmentation, in which various augmentation methods are used to generate the images as shown in this slide. The stage 3 and 4 provide us the sufficient data for training. After this, we move on to the experimentation process, in which we will discuss various architectures. As previously said, data distribution is shown in table 2 is according to the cell type. The given data is divided in training, validation, and test set for experimentation. For each class, we chose only those images which is having the restrictive cell type, otherwise it is discarded. Therefore, for example, among 209 total images, there are only 96 images that contain epithelial cells. In similar way, other distribution is listed here. This is the framework of our proposed approach. In this, when a single image is given as an input, we make the 4 duplicate copies of it, and these 4 images are transformed according to each stain normalization image as discussed in data preprocessing. Now these 4 stain normalized images are given to the patch extraction block, where the patches of images are extracted. The model then processes the input patch and yields the output patch. All the patches of same image are then combined in patch combination blocks. Thus, we obtain 4 different outputs from 4 different models for each single input image. In order to understand the models proposed in this work, we must know the feature pyramid network, FPN. Here is the schematic of FPN for segmentation as proposed by Kirlo, Rosgirshik, and Meteor. The given FPN can be divided as encoder part and decoder part. In the encoder part, features of various resolutions are extracted. After the output of each encoder block, image is downsampled. The output stride of encoder block E1 is E4, for E2 it is 8, for E3 it is 16, and for E4 it is 32. In FPN, all these various size feature maps obtained at each encoder level are convolved to form decoder intermediate block. Each block in decoder intermediate block is convolved and upsampled simultaneously to form decoder block. The dimension of decoder block are 1/4 of the original image dimensions. These feature maps in decoder block are concatenated and further passed for upsampling. Thus, we obtain a output feature map of original dimension in last. In the proposed work, we use two classification models as encoders, that are ResNet34 and EfficientNet B7. The basic building block of these encoders are shown here. Here is the architecture of ResNet34, which is formed by using building blocks as shown before. The different color in architecture represents the change in dimension of image. Thus, we obtain 5 different blocks. Based on the ResNet34 encoder, we design a ResNet34 FPN, whose architecture is shown here. A 5-block ResNet34 encoder, as discussed previously, is used here. The feature maps obtained at each encoder level are converted to form decoder intermediate block. Further feature maps at decoder block are generated by convolving and upsampling the feature maps from decoder intermediate block. At the end, concatenated feature maps of decoder block are upsampled to generate output segmentation map of original dimension. This is the architecture of EfficientNet B7, which is popular classification network. There are 7 different blocks which are formed by using basic building blocks, as previously shown. Here also, each change in color shows the change in dimension. This slide shows the schematic architecture of EfficientNet B7 FPN. The encoder used here is more decoder than ResNet34 FPN. The decoder here works similar to the previously discussed decoder of conventional FPN and ResNet34 FPN. Here is the list of implementation details. We use 16 GB NVIDIA 300 GPU for our experimentation. All the models were trained for 100 epochs with the learning rate of 0.001. We use loss function as dice coefficient loss, optimizer as ADAM, and return the program in TensorFlow 2.0 library. These are the sample results. The above 4 binary images are ground truth annotations, which shows that given input image have 2 types of cells, epithelial and macrophage. The output generated by our proposed approach are shown below. In prediction of epithelial cell, we can observe that model undersegments the epithelial cells. In case of macrophage, some incorrect pixels are also observed along with the correctly predicted pixels. Overall, we can say that our model segments the cells correctly. Here is the second sample image from test set. The second and third model of our proposed approach correctly segments the lymphocyte and macrophage cells respectively. But at the same time, our proposed approach predicts some false positives too, which can be observed in epithelial and neutrophil image of prediction. These are the results evaluated on our test set shown in table 3. The proposed approach achieved a overall panoptic score of 0.4264 on challenge test set. This was a blind test set. Conclusion. We independently segmented the nuclei for each cell type. On combining the 4 different outputs for each cell type, we obtain a single methodology for nuclei segmentation and classification. Though our approach segments and classifies the nuclei, we lack in reduction of false positives for some cases. Among 4 tasks, we obtain a better results for neutrophil in comparison to other cell types. feature pyramid network based on two classification networks that are ResNet34 and EfficientNet-V7 proved to be efficient in segmenting the nuclei of different types. These are the references. Thank you. Below are the contact details.
Any questions for Prasad?
Yes, sir. Can you hear me?
Yeah.
Okay.
Yeah, questions for Prasad.
Yes, we are waiting for questions.
I think we can proceed with the next team then. Our next presenter is Amiraza Mahbood from University of Vienna, and he also requested us to. Amiraza, would you like to present?
You could also play my presentation file. I don't have any preferences.
If you could present, I think that would be preferable.
Okay, then just give me a second to share my screen.
Okay.
Okay, welcome to my presentation. My name is Amiraza Mahbood, and I'm doing a postdoc at Medical University of Vienna in collaboration with Tissue Gnostic. And today I'm going to talk about my development method for multi-organ nuclei segmentation and classification challenge. And the topic of my presentation is sequential unit-based model for segmentation and classification of nuclei in HE-stained tissues. I would consider this challenge as a follow-up challenge for the former MoNuSAC challenge. And in the former challenge, we had the main task of instance nuclei segmentation of H&E stain images at a fixed image magnification and also at a fixed image size. But in this new challenge, beside the task of nuclei instance segmentation, we also have the task of nuclei classification. Again, for H&E stain images at the fixed image magnification, but at various image sizes. There are also other differences between this new challenge and the former challenge, such as in the new challenge, we have various nuclei sizes within the same image, mainly due to various nuclei types. And also we have more color variation in the new challenge in comparison to the former challenge. So in my algorithm development, I use, I utilize dataset for two parts, for performing instance segmentation and the other one for performing classification. For the instance segmentation part, I use mainly three different datasets, as you can see here. I use the training and test set of the former MoNuSAC challenge. I use the training set of the MoNuSAC challenge, and I also use a private dataset from Medical University of Vienna, which had 95 images. And this dataset actually is under preparation, and as soon as it's ready, we are going to publish it. And you can see some sample images that I used in the training phase for instance segmentation. But for the classification part, I just used the provided training set from the new MoNuSAC challenge, which had 4 different nuclei types. As you can see, one example in this slide. And here in this slide, you can see the generic workflow of my algorithm. So it has mainly 3 main stages: a segmentation unit, a distance unit, and a classification unit. And I'm going to explain it in further details in the following slides. I would like to start with the pre-processing steps that I applied on the images before sending them to the network. I normalize the intensity values between 0 and 1. I also create the distance map from the provided ground truths. And also I modified the labels to have better distinction between the touching nuclei. And for this modification, I remove the touching borders, and I also apply an erosion morphological operation. And you can see one example here. And as you can see, after this modification, there is a better distinction between objects. And for the 3 main stages in my algorithm, you can see here a segmentation unit, a distance unit, and a classification unit. In the first stage, in the segmentation unit, I just aim to separate the foreground and background. In the distance unit, I had the aim to find the distance maps of the images in the test phase to find the local maxima and then use them as the seed point for the watershed algorithm. And I also had another network, a classification unit, to assign different types or different classes to each individual detected object in the instance segmentation masks. And here are some parameters that I use for model training. In all three phases, I use a pre-trained network to initialize the weights in the encoder part. I use 5-fold cross-validation in all phases. And I monitor the performance of the model on the validation set for each fold to save the best model. And for the segmentation and classification unit, I monitor the IUS, the intersection over union score, and for the distance unit model, I use MS or mean square error score to find the best model. I also use different augmentation techniques such as random rotation, random horizontal and vertical flipping, random cropping, and also random brightness and contrast shift. I also use test time augmentation to have better results at the end. And you can see also other parameters such as the utilized loss function, optimizer, learning rate, and etc. in each phases of the network for segmentation unit, for distance unit, and also for the classification unit. When I train this model, then I try to merge the results from all these three stages to form the final segmentation results. First, I applied a Gaussian smoothing filter on the results of the distance unit, and the kernel size of this Gaussian smoothing filter was determined by the results of the segmentation unit. Then from the modified distance maps, I find the local maxima and then feed them as a seed point to the watershed algorithm. And I also remove the background from the results of the segmentation unit. So till this stage, I had the instance segmentation results, and finally to assign different labels to each individual detected object, I used the results from the classification unit to perform the classification. I also applied some simple post-processing steps on the results to improve the performance. I removed very small objects, I filled the holes, and I also used the ambiguous masks, which were provided by the challenge organizers, to actually remove some parts of the masks which were not clear in the test images. And here are the results for the validation set for each individual fold and for each individual stage of the model for the distance unit, for the segmentation unit, and also for the classification unit, based on the MSE score and intersection over union score. And here is just a sample results from the test image. So on the top and on the left, we can see the test image. Then you can see the results from the distance unit model. Here you can see the results from the instance segmentation results, the ambiguous mask. For example, for this sample test image, we didn't have any ambiguous area. And finally, in the second row, you can see the results for the classification unit. And here is the results of the test set, which were actually calculated by the challenge organizers. As you can see, I had 2 submissions, and in my second submission, I had around 6.5% improvement. And here are the main changes that I actually did between my first and second submission. So in the second submission, I used 5-fold cross-validation. I also applied test time augmentation, and I also add the segmentation network to the workflow, which I didn't have in the first submission. In the first submission, I just had a distance unit and a classification unit, but in the second submission, I also add the segmentation unit to the workflow. And just by visual inspection of the results of the entire test set, I would say that the general instance segmentation performance of the model was rather good, but the classification part needs to be significantly improved, which we try to address in future studies. That was my presentation, and thank you very much for your attention. If there is any question, I would be happy to answer.
Are there any questions?
Hi, I'm Reza. Thanks for the nice presentation. So my question is, have you thought about integrating these three independent networks into a unified network?
Actually, this is one of my ideas that I want to implement in future, because I had very limited time for this network. Unfortunately, I found out about this challenge very late. So there are many things that can be improved. And this one actually is one of the main ideas that I want to implement in the future, to have these all three stages in one single model.
Yeah, that would be nice. Thank you.
You're welcome. And I have one question, so maybe you can answer from the presentation that most of the teams actually presented. I saw that many people extract different patches, for example, with size of 256 by 256 in a sliding window strategy. But here I also do the same, but I use random cropping in the training phase. Do you think this would be a problem in general, or it's the same method? I don't know if anyone has any idea about this question.
So is your question, is random cropping a good idea or not?
Yes, so for example, if I have like 1000 by 1000 image in the training phase, I just extract a random crop by size of 256 by 256. And when you train this network for a couple of epoch, I assume that this random crop will cover the whole part of the image. But do you think it would be problematic, or it's not?
I think it's just an implementation question. So as you've alluded to, as long as all the pixels are seen by the network, then it shouldn't be a problem. But you also want to make sure that you're not biased towards certain images. So if you randomly crop, that will mean that you have equal probability of a patch being from an image that might be 50 by 50 as an image that might be 1000 by 1000. And that will make your network biased towards those images that are smaller. So that would be the only problem that I can see there.
Okay. Okay, thank you.
Thank you, Mirza, for the presentation and specifying the differences between MoNuSAC and MoNuSAC.
So I stop sharing the screen.
Yeah.
Thank you.
I would like to invite our next presenter, Hasib Zunair, to present his work.
Hello, can you hear me?
Yeah, we can hear you.
I'll just share my screen.
Yes, we can hear you.
Can you see the screen properly?
Yeah, I can see the screen, but it's not in the presenter view yet. Yeah, now I can see.
Now is it there?
Yeah.
Okay. Hello everyone, I'm Hasib Zunair. I'm a first year master's student at Concordia University, and I'll be explaining my method for the MoNuSAC challenge. So this project was done with collaboration with my master's supervisor, Ben Hamza. So I think this is pretty much clarified through all of the slides, so I won't go into this in detail. I will just directly go to what we actually did in the work. So in the first stage, we calculated the height and width for all of the 209 training images. So we could see that there was a large scale variance on the training data itself. And also for the dimensions, we can see that there's a lot of variance between the height and width as well, with the maximum and minimum number of pixels. And some of these images are shown here, which are at actual scale. So this demonstrates the large scale variance that is present in the training data. So to make it more challenging, the data set also had a large imbalance between the 4 classes. So the balance was almost between a ratio of 20, like the highest number and the lowest number of cells. So there was a severe class imbalance in the data set as well. So in order to address these challenges, we initially posed the problem as a multi-class semantic segmentation problem. And this is followed by a post-processing to get the instance level segmentations from each of the classes. We implement a patch-wise training scheme to address the large scale variance. And for training the network, we use the weighted combination of multiple losses to address the data imbalance. For the network architecture, we use a UNet with a pre-trained backbone, which I will go into detail in the later slides. We also tried different backbones, but the one we used here proved to give optimal performance. For creating the patch-wise data, we extracted 96 by 96 dimension of patches from the whole slide images and as well for the masks. And we used reflection padding for any patches which were less than 96 by 96. And also when we took the patches, we found that the images, like many of the masks had almost like less than 10% of the foreground pixel. So we discarded them initially before running the training scheme. So after that, we had around 250,000 patches from the original 209 whole slide images which were provided for training. And we use a 80-20 split for training and validation. So this is the model that we used. So initially in the encoder, we use an EfficientNet B3 architecture, which is pre-trained on ImageNet. And this whole entire architecture is based on a UNet architecture. And for training this network, we use a multitask loss function, where we initially use a Jaccard similarity, which is converted to a Jaccard dissimilarity for minimizing the loss. And we also use a weight term in the Jaccard loss, where the weight is assigned with 0.5, 0.5, 2, and 2 for each of the classes. And these numbers were found by experiment. We also use the focal loss, which is well known to address data imbalance for any classification or segmentation tasks. So we combine these 2 losses and add 2 regularization terms, which is 1 and 0.5. And also these numbers were found with respect to the validation set. For training, our goal was to minimize this loss function. We used the Atom solver with a learning rate of 10 to the power minus 4 and a batch size of 128. And these numbers were also found by experiment with respect to the validation set. And we train all of the layers and monitor the Jaccard index, and we use early stopping to avoid overfitting problems. We also tried data augmentation, but it did not prove quite well. So in our final submission, we did not add any data augmentation. For inference, we used non-overlapping predictions with a sliding window size of 96 by 96. We tried overlapping predictions, but the results were rather poor. And after that, we used a median filter with a sigma value of 5 to improve the segmentation masks, as some of them were very noisy. And then the segmentation masks are converted to Boolean masks for each of the classes and their input to a watershed transform to get the final instance level masks. These are some results where first we trained a UNet architecture, and afterwards we trained the UNet with an EfficientNet B3 backbone pre-trained on ImageNet. And lastly, we used the multi-loss term to see the final results. Here we show some outputs from the multi-class segmentation model. So over here, it can be seen that it performs quite well, but when we do the instant segmentation, we have some problems over there that can be seen from here. So from this figure, we can see that the entire model or the entire method suffers from over segmentation on each of the cells of the nuclei. So future works would suggest to come up with better post-processing stages so we could like reduce the over segmentation problem, and we would also aim to use pre-trained networks on medical imaging datasets rather than on natural images such as ImageNet. So if anyone is interested on the codes for this work, it is available on GitHub at the link below. Thank you, everyone, and I'll be taking questions now if there's any.
Any questions for Hasib? Okay. Thank you, Hasib, for the presentation.
Thank you.
Now I'll invite Stephen Smiley for the next presentation. I think he's not here. Okay, so I'll present his video pre-recorded video presentation, and this is the last presentation we have.
Hi, this is Stephen Smiley. This is my presentation for the multi-organ nuclei segmentation and classification. That's the MoNuSAC 2020 challenge. And the name of the algorithm that I put together is CRF4 X-ray Tech UNet, which is the very famous biomedical image segmentation algorithm that references are in my manuscript I provided. So the credit goes to them for that portion for UNet. And that's Ronenberger, Fisher, and Brox. So I'm going to dig into how I was greatly inspired by their algorithm to put this together to attempt this challenge. And let's get in. So from a high level view, this is a flow chart of my algorithm. The top is the pre-processing. The middle is the meat and potatoes, the methodology, the UNet architecture, inspired UNet architecture, and the post-processing, which uses Oscar, Tango, Sierra, Uniform, that's ASU thresholding. So looking at the top of that flowchart at a lower level, where you can see what's going on, you have the data pre-processing step. The first thing to do is, after you've gotten the images for the challenge and have them on your computer, import them into your notebook. So I ran the Google Colab to do this competition, the pro version with GPU setting, high RAM, and after I had that kind of set up and I had the files I needed to run this algorithm and train it, I was able to start importing them. So the first step in the pre-processing is resizing and zero padding. And the reason I say those two right there is because they came in different flavors, different sizes, and not all of them were uniform in class. And the classes are macrophages, neutrophils, lymphocytes, and epithelial cells. So I'll show you the code and kind of how I was doing that. So there's quite a few libraries I used. What I ended up hard coding and going with was 2 times 128. 2 times 128 is 256 image width and height. Here's the locations I had put them on the Google Drive to import them from. Just verifying that I was using the GPU with TensorFlow on the Google Colab Pro. I'll show you the functions for that resize and pad. So 256 would go in that base width. You could reshape and scale basically from an input image. This function for padding, numpy, np, zeros were the reference array, or not the reference array, but they formed the gap. So when I actually imported like these test images, they weren't 256 by 256. They could be like a little over 400 by a little over 800. Then I would rescale with the scale with the resize function to 256. You would have a side, the smaller side, not at 256. So you would pad it, and I would have a square now. So every image was consistent and same size with a zero padding to feed into those units, inspired units. Same thing with the training. You would, I would feed it in and have that padding. It's 256 by 256. Difference here, some patient IDs, so like this patient, Tango Charlie Golf Alpha 86, TAC 8672, TAC 01, Zebra, TAC 00, TAC Delta X-ray 1 underscore 3. This one had neutrophils and lymphocytes, epithelial, but no macrophages. So there's a class imbalance right off the bat. You can see it. And you can verify kind of what patients have what. And you can also see the different flavors and how these neutrophils and lymphocytes and all these cells look, because sometimes they come in different colors and different just kind of variations of the same thing. And when it comes to training a neural network, you kind of want to make sure you have enough data. And so if this one only had 209, I believe, was the total input images, with even smaller or even fewer for a given class, then data augmentation was probably a very important step, or at least one of the more important steps to get some sort of accurate prediction. For instance, segmentation, which is really what this challenge was going for. So after I kind of had all the files in this notebook running, I could see like there's 58 macrophages, there's like 94 neutrophils, 146 lymphocytes, 96 epithelial. So that's kind of, that was my class imbalance to start from. So if I go back over here to the data augmentation step in the flowchart, performed random rotations, random horizontal and vertical flips, and random variations on zoom and brightness. And zooming out, you have each one of those would end up feeding a single unit. So go back out. So this is the data augmentation part. Keras, TensorFlow, they have this function called the image data generator. And that allows you to do these random rotations and flips, and zooms. And so I had that specified here in this function I defined called image generator. And then I was able to actually make it come into this other function and basically ensure there's at least 1,000 output. So that was how I accounted for class imbalance, and I would check it, you know. So 58 macrophages, you have 1,073 coming out to train its own respective unit. Same with neutrophils and epithelio and so forth. One key to this problem was, like, if you're going to use that data augmentation function from Keras, then you want to do this random seed setting like after you do that. And this is just so that way you can actually have a consistent model. Like, if you don't set the random seed to a set state, then every time you try to go back and see what you did, you might not be able to see the same results. I mean, it'd be close, but not the exact same. So that's why I set it like that. Here is the UNet model architecture. It has a 2D convolution, dropouts to prevent too much overfitting, and ReLU activation function. Max pooling, so it's picking the maximum value within that 2x2 filter. It's going through until it gets to the bottom here. And it comes back up with the transpose. And it's fully connected when you have these, what is it? When it's multiplying like a C. So if you look at these U's, like U6 and C4, well, C4 is over here, so it's fully connecting it over here. So this is kind of what is the beauty in the architecture of the unit. I use the Atom optimizer with a loss rate at 0.001. I tried several different loss rates, and this one just seemed to work well enough. Just looking at the outputs, dice coefficient, accuracy, and mean squared error were the metrics I used when I compiled. And I used binary cross entropy because I was dealing with the sigmoid activation function for each class. That meant that the output was between 0 and 1. So it would make a mask, it would make a binary mask pretty much. And I was going to use a function to optimize a threshold based on the panoptic quality. So the panoptic quality, that was the metric used in this competition to evaluate how good our algorithms were, or really models. And this threshold finder that I put together just went and did a search to kind of see what was the appropriate threshold based on the training images. And so, like, you can see the threshold of 0.13 optimized that training for macrophages to a PQ panoptic quality value of 0.17. And that is just for the semantic segmentation at this point in the code. And I can show you that on this flowchart. So as we've gotten past here, we're in the post-processing step. And like I said, I have 100 epochs set, atoms, learning rate, set binary cross entropy, sigmoid output, the optimized metrics, dice accuracy, mean squared error. All right, so this is where I was just showing you in the code. There's binary thresholding using that panoptic quality. And that's post-processing. It's done on each one. And these steps, like 3.1.2 and down, are more for the instant segmentation. So after I've trained all the networks on the training data, and I'm ready to start looking at the instant segmentation, which is further down. I believe this is where it kind of starts. I would perform this Gaussian. This is from Open Computer Vision CV. Threshold, ASU, It's another function of OpenCV. And these things in series with region props would allow me to get the instances. So to give me an actual number for every instance, like 1, 2, 8, you know, all the way up to the maximum number that it counted. And you can see how that kind of works. So not the best here, right? Like, see how they're all kind of glued together. There's probably some better post-processing things like water shedding. I didn't use that and just ran out of time. So I did what I used. Probably is why my results weren't the best, but hey, at least I did it right. So did that for each one. This is just showing the training and validation. Once I get to actual testing, we are provided a, what's it called, ambiguous mask. So there are certain portions in these images that we found out in the competition that weren't great at making our predictions. So we were provided midway this ambiguous mask file. So basically, if we predicted something, you could cut it out, like shown here. That way it didn't go against you when they were evaluating the PQ values for the leaderboards and the overall competition results. So yeah, you can see in this example for the test, just kind of what it's seeing. It's saying, all right, here are your epithelials predicted. Here's like the mask image, subtract. Here's kind of what the instance segmentation would be. So this is basically in a nutshell what I did in this competition in order to get the results that I did, which you kind of see here. And for me, on my training data, I had like a 0.52 for the macrophages, and validation was like 0.16, and neutrophil 0.6, validation 0.26. I could definitely tell that I overfit to my training data, and probably with more time and more epochs and maybe a different post-processing procedure, I could have got better results. But I think it was, like I said, pretty fun, and I'm happy to have been able to participate in this competition. So hope you enjoyed, hope that made sense. Thank you.
Are there any questions? Is a general discussion with all the, with everyone, is that part of the agenda, Ruchika?
I was going to talk about the manuscript details again, and then if everybody wants to connect again, we can find time.
Just like 5-10 minute conversation with everyone. Just wanted to get their experience with the competition and all that.
Yeah. Do you want me to talk about the manuscript details again, and then
Yeah, let's quickly talk about the manuscript details, and then we can have a little bit of a free discussion.
Okay. Thank you everyone for such interesting presentations. I would like to talk about the manuscript details again. We are going to draft a manuscript after this workshop, and the models which are appearing in the final rank list will be described in the manuscript, and all the participants will be acknowledged for their contribution through an authorship in the publication. I also want to inform that we are accepting post-challenge submissions, and the due date is April 30, and it's only for those who didn't submit yet. And if anybody is interested to participate, feel free to register, get the data, and submit your results. If you have any questions, please write to monusac2020@gmail.com. I would also like to know if there is any feedback about the challenge or anything you want to say to us.
Any feedback? So let me ask a question. How was your experience with fine-tuning models using the NVIDIA cloud access? Did that work out for some of you? you'll have to unmute yourself. Everyone is muted.
Oh, okay.
Sayed, you were saying something?
About the NVIDIA credit, we first tried
Sayed, you were
using it,
saying
but
something?
yes, about the NVIDIA credit, we first tried using it, but there was a time limit on the session that we could have, and so I think it was 10 hours. Am I right?
Yes, you're correct.
So, well, because of that, we didn't really put so much effort into using it. I think if you extend the time limit, it would be a lot better.
Sure. So your point is
Thanks.
taken. We'll send this suggestion to NVIDIA folks.
Thank you very much.
Thank you. Any other feedback?
So I want to ask a question to everyone. Go ahead. So my question to all participants is, have you guys already compared color normalization versus color augmentation, and if so, what are your conclusions? So I see two different conflicting results on this, comparing the two approaches. In some papers, I see that color augmentation works better. In others, I see that people are still trying color normalization.
So my findings are that personally, I think that, well, it completely depends on the data set, doesn't it? But my experience is that color augmentation is sufficient. But like I said, that can completely depend on the problem, and also it depends how significant the color variation is. So there's a paper that shows that actually when you stay normalize and then you perform augmentation on those stay normalized images, that might be the best thing to do. So I think potentially the combination of both could be quite promising. So that's a paper by David Tellez from Netherlands. I can post it in this chat in a second if you want.
Sure.
From my experience, I did try both of the techniques. So I think in this challenge, the main issue that I encountered was the color profile difference. So when I normalized my training data to the testing images, the color normalized images were very strange. I believe it's because the testing images, the channels are not RGB but BGR. So I think in my experiment, the color normalization didn't really work because testing images, the color split. But I think as Simon pointed out, usually the color normalization and augmentation, combining those two techniques, will perform the best, I believe.
Thank you. Question?
Sir, your voice, I think there's a lag in the internet connection. Didn't hear you.
I was asking, I was saying thank you. If anyone else has any general questions for discussion, maybe they can ask now.
I wanted to ask a question. In color normalization, how do you choose your target slide?
So for us, we usually look at what you can say is subjective best quality slide, which gives you the best contrast between, let's say, nuclei and the background or cytoplasm, or whatever you say. So it's visually that gives you most distinctive characteristics of the tissue. That's how we choose.
I would say where you can see visually clear differences between the nucleus and the cytoplasm. There, where you can see pink and purplish, like if it's more clear to you, then I think that's a good image.
Thanks.
I have a general suggestion. I don't know if you read it from the chats, but would it be possible for the organizers to measure the general instance segmentation performance of different approaches, not just disregard the classification parts, to have something like a binary PQ, and just as extra information?
Yeah, we'll compute PQ. I don't know if we will compute PQ for that. If we have to just evaluate the segmentation performance, we might use AGI or something else to compute the segmentation performance. But we'll do that. Thank you for the suggestion.
I think PQ for binary performance still is a very good choice, personally, especially if you've already used it now for multi-class. It translates perfectly across to binary.
Yeah, we can do that, but the problem with PQ we do not want to penalize for false positives in that, because then there is no ground truth. So all the so the PQ will just penalize the count of the number of false positives. It will not penalize for the pixels belonging to how many pixels were false positive in that particular instance. So that's why AGI will penalize that heavily.
For example, if you have a false positive which is very big in size, your PQ will only measure it as a single instance, and then it will go in the denominator as one instance. But you are not going to get a heavy penalty on that. So that's why we are thinking like there should be some metric, maybe AGI or something else, a modified AGI or anything, which can penalize the pixel level variation. If there are more false positive pixels, so there should be low value for the metric. And in PQ, I think that there is the differences are not too much between the two examples.
If you have a bigger false positive versus a smaller false positive, that PQ doesn't distinguish. So we want to incorporate that in the error metric for if we want to just evaluate the segmentation.
And I would also know your comments if you have any information about this or any other suggestion on this.
I mean, I'm in favour of binary PQ, but I mean, I don't want to open a can of worms here, so it's your choice at the end of the day. But I'm very much in favour of PQ as a metric, so I'm happy that you guys use that. And I would also say that I would prefer it for the binary segmentation performance as well. But of course, it's up to you at the end of the day.
Sure. Thank you. Anything else?
Maybe the way that you measured PQ and the way that Simon measured the PQ is different, because also in the validation set that Simon shows in his presentation, I think the scores were much lower compared to what was reported actually in the test phase of the challenge. So maybe there are two different ways to calculate the PQ. So maybe
I think I know the difference here. So we would have calculated PQ in the same way if we assumed that if we took, for instance, calculate the PQ for a given class, the score would have been the same, but the difference would have been how we deal with the negative cases. So for example, if there is an image where you have, for let's say neutrophil, the ground truth is completely blank and the prediction is completely blank, how do you deal with that case? And I think I just skipped that example. So therefore, I'm guessing maybe you guys assume that would be 1 for a PQ score, but I assume that was 0. And I think that's the difference in the scores.
Yes. So
I just want to make it clear. Do you mean that you are not computing class-specific synaptic quality, but from the overall image?
So I think the difference is, I guess it's a question for you really. Imagine if you had a blank image. So let's say for neutrophil, the ground truth was blank. And then the prediction was blank as well. I mean, what would you do in that scenario?
Oh, so we compute the panoptic quality for each class separately. So if you have we do not allow mixture of classes.
Okay.
So that's what makes the difference. So we separate each prediction into a separate prediction for each class into a separate folder, and then we compute PQ.
And
Right. Okay, that makes sense. Yeah. So yeah, that's definitely different to how I've done it. So that explains the difference in my validation results, and yeah, so that actually makes quite a bit of sense. Okay, I understand that now. Thank you.
Any other questions?
All right, we'll be in touch. If you have any other questions, please email us. You have the email at monusac2020@gmail.com, and we will we'll start putting this together for the paper, and we will we'll be communicating with you through the emails now. Thank you so much for taking the time for this presentation and submitting your results, participating in the challenge, and we'll keep you posted. Thank you. Bye bye, everyone.
Thank you so much for your effort.
Thank you so much.
Bye.
Thank you.
Thanks, everyone. Stay safe.
Goodbye, everyone.
Goodbye.
Bye.
Bye-bye.
Bye.